All right, this lesson is on scientific notation. By the end of this lesson, we hope that you'll be able to change numbers from scientific notation to standard form and vice versa, and also know how to multiply and divide numbers in scientific notation. All right, so let's start out with some key terms. Standard notation. Standard notation refers to how we're used to seeing numbers written, right? It's the number written out in its entirety without any rounding. All right, so some examples of that are 1,254,000. This 0.006589, 3.458. Any number that's written out in its entirety without any rounding is called standard notation. All right, now, scientific notation is used to easily write both really large numbers and extremely small numbers. It's a number written as a power of 10, right? So it's written as a power of 10 because our numbers are in base 10. Meaning that if we multiply a number by some power of 10, we're just moving the decimal around either to the left or to the right. So it makes it really convenient for us to write really large numbers as a power of 10 or really small numbers as a power of 10. All right, so when we write something in scientific notation, we have two numbers being multiplied together to make up the entire number in scientific notation. Right? The first number is a number between 1 and 10 absolute value wise. So we have a number in front between 1 and 10 absolute value wise being multiplied by a power of 10. So it's 10 raised to some power, which is an integer. So there's always two parts to it. So here's some examples of some numbers written in scientific notation. So notice this first number here, 1.98. That's a number between 1 and 10. And then we're multiplying it by a power of 10. So yes, if you wanted to change this back to standard notation, right, you could get on a calculator, follow the order of operations, raise 10 to the ninth power, and you get a number that's like a billion, and then multiply it by 1.98 and get your new number. So here's another number written in scientific notation. Notice that first number again, 9.32. That's still a number between 1 and 10. This number can't be like 93, or this number can't be zero point 0.9, right? It has to be between 1 and 10. And this is always 10 raised to some power, and that power up there is always going to be an integer. So it can be positive and negative, right? But it can't be a decimal of a number, right? We can't have a fraction up here or a 0.32 or a 1.2, but it can be a negative 2, for example, as we will see in our examples. So let's take a moment. Can you think of something that would be better to write in scientific notation rather than standard notation? I mean, why are we learning this? If I can just write it how we always would write it, why would I want to write something in a different form? So remember we talked about something being really, really big, or a lot, large measurement or a lot of something, or something maybe really small. Let's take a moment to pause the video, see if you can come up with some examples. There are many. All right, so here's an example of maybe something that could be really large. Let's say I was talking about the number of stars in that galaxy. Or how about the number of stars in the whole universe? The number of stars in the sky, how do I count thee? I wouldn't want to write out that number in standard form if I was doing for the entire universe, because we might have a number with a one followed by many, 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 many zeros, and it'd be really cumbersome to write. I think there's something like 7.2 times 10 to the septillion stars. So it's quite a lot. We could also be talking about the distances, right, between different galaxies in the universe, maybe in miles. Think how many miles it would be from the Milky Way to the next nearest galaxy. It's about 4 light years. How many miles is that? Well, a huge astronomical number that I don't want to write out in standard form. And so that's why it would be useful to write those kind of things out as a power of 10. Look here on the picture of the right. We have a picture of some bacteria. So if I were talking about, well, how big is this bacteria? How wide is that piece of bacteria there? And I was talking about it in feet or meters. I thought it'd be really small. right? It's microscopic. You have to have a microscope to see it. So this might be like 0.000000001 meters. Well, that's another cumbersome number to write. Maybe I could also be talking about how much this one bacterium weighs. That'd be a small number too. So that I might want to write something like that using scientific notation. So that's what we use it for. And that's why, in fact, it comes scientific notation means something to do with science. Yeah, it's how scientists measure those things that are really big, write those kind of numbers or write numbers that are really small. So you'll see it when you come to your chemistry class if you haven't already. All right, so standard notation to scientific notation. So let's take a number, like this really large number here. So this looks like 1,980,000,000. Let's go ahead and change that to scientific notation. Remember, our goal is to write it as a number between 1 and 10 multiplied to some power by some power of 10. The way that we do that, right, is we're going to get a number between 1 and 10 by moving this decimal place to the left. Remember, after a large number like this, there's always a decimal, even if you don't see it, right? And we can move it, and we count how many times we move it until we have a number that is between 1 and 10. So see right here, if I take this decimal and I move it in between the 1 and the 9, then I have a number that's between 1 and 10, right? It'd be 1.9. Basically, you're moving it to the left till you just have one number to the left of the decimal. You can think about it that way as well. So here's our 1.98. And then we're always going to have times 10. And then now to get this exponent on the 10, you simply count how many times you had to move that decimal to get it between the 1 and the 9 in this case. And it was 1, 2, 3, 4, 5, 6, 7, 8, 9 times. So then 10 to the ninth power. And yes, if you went ahead and typed that in on a calculator, you could get that number back. Right? 1.98 times 10 to the ninth power is this 1,980,000,000 number. All right, so take a moment, pause the video, see if you can write this number, which is in standard notation, see if you can change it into scientific notation. All right, so I had to move the decimal back. It looks like 1, 2, 3, 4, 5, 6 times. All right, so then I simply am going to write 5.436. So all the non-zero digits, notice that we write here as the first number. And then times 10 to, yes, we had to move it 6 times, so it's 6. Notice, and this should make a lot of sense, that large numbers have positive exponents on the power of 10. Right? Because if I take 10 and raise it to some positive exponent, it's going to be a big number. And then I take that and times it by another number, I'm going to end up with another big number. So the way I like to see it is when you see something in scientific notation and you see that it has a positive exponent on the 10, then you know that's representing a really large number. Right? And you can actually look up the powers of 10 and know if you knew this, you would know that 10 to the 6th power, we call order of magnitude 6. Means that something is in the millions. When I see a 9 as the power on that 10, we'd say that number has order of magnitude 9, which I know means it's in the billions somewhere. Now let's go the other way. Let's take something in scientific notation and change it to standard notation. All right, so here we have a number written in scientific notation, 2.3 times 10 to the 4th power. Once again, yes, you could pull out a calculator and you could take 10, raise it to the 4th power. I know that something that has order of magnitude 4 here is going to be something in the tens of thousands, right? Because this means a 1 with 4 zeros behind it. It literally does. So a 1 with 4 zeros behind it is 10,000. And then I'm taking 10,000 and multiplying it by 2.3. Well, 2.3 times 10,000 is going to give us 23,000. Right? So I already know what the answer is, but we know it's going to be bigger number, right? Because we got a positive exponent. And positive exponents tell you to move the decimal to the right. And just like before, you can just look at that exponent and it tells you how many times to move it to the right. And so I'm going to move the decimal to the right 4 times in this case. So here we go, 1, 2, 3, 4. And notice where I have empty spots there, I fill in with zeros. And now the decimal is moved from here to here. So our final answer is 23,000, just like we would have got on the calculator. So again, we have a number like this. It's real easy. I look at the exponent of 8. Oh, that means move the decimal to the right 8. And I know that I should end up with a big number because I have a big positive exponent there, right? And something to the order of magnitude 8 tells me it's in the hundreds of millions. Just by looking at that exponent, I know that. So let's see what we get when we move this to the right 8 times. All right, so we move it to the right, and notice how I'm filling in the zeros for the places where I didn't have anything. So we're adding those zeros. And we end up with 365,900,000 in standard notation. All right, so basically when the exponent is positive, the standard notation is going to be a large number. Let's talk about negative exponents. Let's do it with negative exponents this time. Let's take something in standard notation and change it into scientific notation. All right, so standard notation is just the regular way you're used to writing numbers. And here, notice we have a small number. We have after the decimal here, we have 1, 2, 3, 4, 5 zeros, and then 369. All right, so this is a small number, and we can use scientific notation to write things that are really small. So in this case, I still need a number, right, that's between 1 and 10. That first number we write has to be between 1 and 10, absolute value-wise. So I move it until I get just one number to the left of the decimal. So notice how I stopped this time after the 3. I don't go after the 6 right to the 9, right, because then I'd have 36.9. We can't have that. We have to have a number between 1 and 10. So I stop as soon as I have one non-zero digit to the left of the decimal. In this case, right there. And so we get 3.69. And this is very much like it was when we did it with positive exponents. I do count how many times I had to move that decimal to get it between the 3 and the 6 in this case. And it was 6 times. But now the exponent, notice how it becomes negative. All right, so when you see those negative exponents, that tells you that we have a small number. And so when we're moving the decimal to the right, if you want to remember a rule, that's when we get the negative exponent. So take a moment, pause the video, and see if you can write this number in scientific notation. All right, so in order to write scientific notation, I need that number between 1 and 10. So I put my decimal right there between the 9 and the 6. How many times did I have to move it? Well, we can see we moved it 1, 2, 3, 4 times. And then you should have made sure to put 10 to the negative 4 power. Right? If you're confused, if you're trying to memorize rules about when is it negative and positive, just look at the number itself. Small numbers have negative exponents. Big numbers have positive exponents. So we have small numbers here. So we know that the exponent should be a negative number. All right, now let's go the other way. Let's reverse that. Let's take a number that's in scientific notation, a small number like this, right? I know it's small because of that negative exponent. And let's change it into standard notation. All right, so negative exponents, now this time we're moving to the left. We're moving the decimal to the left however many times we need to as indicated by the exponent on the as the power of 10. All right, so before we were moving to the right, now we're going to move to the left to make this number a small number, right? And add zeros as needed. So let me demonstrate with this example. We have 3.6. I'm going to move that decimal to the left 1, 2, 3, 4 times. I fill in the zeros. There's my new decimal point, and then there's my new number in standard notation, 0.00036. Take a moment, pause the video, see if you can write this number in standard notation. All right, since we have a negative exponent, that should have been telling you to move the decimal to the left. In this case, 6 times. So we move the decimal to the left 6 times. We fill in those zeros. And we simply write our new number. So again, to summarize, when the exponent is negative, it's representing a number that is very small in standard notation. So now let's talk about performing some calculations in scientific notation, right? Multiplying and dividing. This becomes useful when we have really large numbers in scientific notation or really small. And if you try to maybe change those numbers into standard form, so one idea would be, well, let's just change it to standard form and then perform the operations like we always do. You can do that, except for sometimes the calculators won't give you an answer that you're used to seeing the way that you would like to in standard notation, either because it's so large or so small it can't write it that way. Right? And I'll show you on the calculator when you see that little e at the end and then to some number, that's how they use write standard or excuse me, scientific notation on the calculator. So performing the operations using the standard notation instead of converting them is going to keep you from having those kind of calculator errors. First of all, when you have numbers again so big and small, it's hard and gets really cumbersome to write them out and do that. I don't want to try to type in a number on my calculator that might have 23 digits. It might not even take that number. That's why we have to learn to do it this way. All right, so rules for multiplication. Okay, when multiplying with scientific notation, all we do is multiply the coefficients together. So that first number between 1 and 10 that we were talking about, you just multiply those like you always would normally. And then we add the exponents, and then the base, of course, is going to remain 10. So this is just an application of the product rule for exponents, right? Which says that when we have the same base, we add the exponents when we're multiplying, right? So let's do a few examples, all right? So we're going to multiply numbers written in scientific notation. So we're going to multiply that first number out in front and add the exponent. So take a look at this problem here. 3.2 times 10 to the negative 3 times 2.1 times 10 to the fifth. Going through our rules, all I do is multiply these numbers out in front. Okay, so I jump on my calculator. I do 3.2 times 2.1. And when I do that, right, we're going to get about 6.7. And then we add the exponents. Remember our product rule for exponents is here's the same base, right? They have the same base of 10. So then I should be doing negative 3 plus 5, which is a positive 2. So now this answer is 6.7 times 10 to the second power. And so multiply in front, add exponents. So let's do one more example, and then I'm going to have you do a couple of practice problems. So here I'm multiplying two numbers written in scientific notation. All right, step one says let's multiply the numbers out in front. So in this case, the 8.2 times the 5.1, we times them together. And then I'm just showing you, I'm rearranging this to show the powers of 10 being multiplied together over here. All right, so when I do multiply 8.2 times the 5.1, I get 41.82. Right, and then over here, I know that's going to be times 10 to, I should add the 8 and the 3 to get, we're going to add them and get 11 eventually. So let's do that here. So now I have 10 to the 11th power, right? That's easy enough. We can see we got that from adding 8 and 3 to get the 11 here. We can see how we got 41.82 by multiplying those numbers out in front. The only problem is this number right here, right, is not in scientific notation because this number in front has to be between 1 and 10 absolute value-wise, and it's not, right? In order to make this number between 1 and 10, I need to move that decimal to the left. So I'm going to go ahead and move it to the left so I can write this number as 4.182. Now I'm happy, right, because it's a number between 1 and 10. But notice what I did to the exponent. Right? Just like before, if I'm moving that decimal to the left, right, then I need to add to the exponent, right? It's like we basically times it by a power of 10 or divided it by a power of 10, right? So we need to take away 1 power of 10 if I'm moving that decimal to the left. So if I do that, then I need to add to my exponent. So just remember, if I have to move it to the left, add to the exponent. I moved it left 1, so I added 1 to the exponent of 11 and got 12. All right, so take a moment, pause the video, and see if you can work out this problem. Remember, use scientific notation to get the answer. All right, so we should have just said, hey, let's multiply the numbers in front. So in this case, the 2 times 3. That gives you 6. Hey, keep the base of 10, right? This is how we multiply when we have exponents, right? With the same base, we just add the exponents. So it's times 10 to the 3 plus 5, which is, of course, 8. And we get the final answer of 6 times 10 to the 8th power. And so in this case, since we had a number between 1 and 10, right, the 6, I didn't have to mess around with moving that decimal around anywhere. Right? It was already in how I liked it. Let's try this example. All right, so the rules say let's go ahead and multiply those numbers in front. We're going to keep the base of 10 and add the exponents. So let's do that. So negative 9.3 and negative 9.3 times 4.7 gives you negative 43.71. Notice how I still follow the rules for multiplying integers or the rules for adding integers. Those never change. And those never change. So a negative times a positive is still a negative. And then over here, a negative 9 plus 3. Okay, the signs are opposite, so I should subtract those numbers and keep the larger sign. So negative 9 plus 3 is negative 6. Okay, so we've just followed the rules for multiplying and dividing and adding and subtracting integers here to get this answer. And then now, like before though, notice that this negative 43.71 isn't a number between 1 and 10 absolute value-wise, right? I have to move that decimal again to the left. So notice I move this decimal to the left, and then I have to add 1 to the exponent. So remember, and this is, be careful with your signs when you're working these out, a negative 6, if I have to add 1, negative 6 plus 1, that's how we get negative 5 here as our new exponent. Right, because moving to the left adds to the exponent. Add 1 to here. And so that one was a little tricky. Remember, just make sure that you are following all those rules that you learned, right, all the way since the 4th or 5th grade about how to multiply and add and subtract integers. Now let's do an example where we're doing division. So division is very, very close to multiplication. Right, so remember how we were multiplying those numbers in front? Now we're just going to divide those numbers in front. And then before we were adding the exponents, now we're going to subtract them. Why are we subtracting? Because remember when we're doing a division problem that involves exponents, we have something called the quotient rule of exponents that you learned in the previous lesson, which says that I have to take the numerator, the exponent in the numerator, and subtract away the exponent in the denominator. That's why we're subtracting them. And of course, the base remains the same. If the base wasn't the same, that base 10, one, they wouldn't be written in scientific notation. But two, we couldn't apply that rule where I just subtract the exponents. All right, so let's do an example here. Let's work through it. Suppose I have this problem. Divide 6.4 times 10 to the 6 by this. All right, so I take 6.4 and I'm just going to divide 1.7. And then I'm going to take my exponents, right, the top one, which this number is in the numerator here. So I'm going to do 6 minus the 2. And that's it. So 6.4 divided by 1.7. I go on my calculator, I get 3.8. And then I do 6 minus 2 to get the 4. So this answer is 3.8 times 10 to the 4th. Pretty easy, right? Just like the multiply. Let's do an example like this one here, where I'm going to end up with a number in front that is not in standard form, how we like to see it. All right, so applying these rules, I just divide those two numbers in front. So I do 2.2 divided by 8.3, and I get this 0.265 number. Okay, following the exponent rules, right? I take the top exponent minus the bottom. So 8 minus 11 is -3. Again, here's the problem. That number in front has to be between 1 and 10, absolute value-wise. So I don't like this 0.625. So in order to get this number between 1 and 10, right, I need to move that decimal to the right. That's effectively saying I need to multiply it by 10, right? So when we do that, this time we subtract then from the exponent, excuse me. And so when I have to move that decimal to the right, we subtract from the exponent. So we had -3, and then I minus 1 to get -4. Right? This makes sense. So when I had a number where I had to move it to the left, right, we added to the exponents. And if I have to move it to the right, we subtract exponents. So if you need to write that down in your notes to keep it so you can remember at first, go ahead and do that. But you can find that out just by playing with the calculator, right, that these two numbers are actually equivalent. Like if I wasn't sure, I could go ahead and multiply that out on a calculator and get the standard form for it, compare it to this one, just to guarantee they were right. So if I was confused and I didn't know, I would try an example like that for myself and see which one to do. And so take a moment to pause the video and see if you can divide these two numbers written in scientific notation. All right, so you should have just been taking the numbers out in front, dividing them, then applying the quotient rule for exponents, subtracting the exponents on the base of 10 here. So when I divide these two numbers, I get -2.1. Remember, we still have to follow the rules for exponents. If you get a negative number out there, you get a negative number out there. That's okay. The nice thing is, notice that it's a number between 1 and 10, absolute value-wise. So I'm happy. We won't have to be moving the decimal around after this. All right, and 9 minus 5 is 4. So we get -2.1 times 10 to the fourth power. All right, so in this example, right, we're going to start here. Suppose I had this, right, and I'm going to go ahead and divide the numbers out in front. So when I do that, I get a negative divided by positive is this negative decimal of a number here. And I wanted to have a problem like this, where we had a positive exponent here and a negative in the bottom, to show you that when I subtract those numbers, right, I am doing 12 minus a -6, like this. Remember, when we have the opposite of a negative or a minus, it becomes a plus. So this is the same as saying 12 plus 6, which is a positive 18. That's how I get positive 18 right there. All right, but here's the problem. Here again, I have a number that's not between 1 and 10 absolute value-wise. I'm going to have to move that decimal 1 to the right. Okay, so if I move to the right, I subtract from the exponent. So it comes from 17 to 18. All right, and that concludes this lesson. If you're watching this as a recording, make sure to go back into the course announcements and answer the question form.